technical software engineer working in the Emerging Technologies Organization in the office of the CTO at Red Hat. And I'm so sorry I couldn't be there with you. My flight was canceled and there wasn't any other alternative for me to get there, but I wanted to be at least virtually. I don't know if we will use this recording or a live session. Let's see. So I guess Tom has already introduced the talk, so let's get right into it. First, I'm going to talk about the Gateway API Inference Extension. This is a Kubernetes project that provides artificial intelligence awareness to the Gateway API. So I want to emphasize that this is basically a protocol that allows you to reuse your traditional gateways, like Envoy, for example, and into what we call an inference gateway. An inference gateway is a smart proxy designed for routing your AI workloads in an optimal way. And it's very important to highlight as well that it's extensible, so you can write your own policies. In LLMD, a project that I will mention later in the presentation, we have an implementation of this protocol called the Inference Scheduler, where we make use of the Gateway API Inference extension and add specific features like scores, filters, and so on. Some of the benefits of this inference extension is that you can direct requests based on model names, including support for fine-tuned models. You can prioritize latency sensitive tasks, perform gradual model updates, doing traffic splitting, utilize real-time metrics for model servers to do intelligent routing, all these kind of things. So the flow, it's like this. A client sends a request, like a standard get / completions request, and the Kubernetes gateway selects a set of servers based on what we call the inference pool. Then it picks the right model server based on a specific criteria, and finally the request is sent to the model server to perform the inference process. This setup allows us to move beyond simple round robin and make intelligent real-time decisions to optimize our workloads. This is the configuration of the Gateway API Inference extension, right? In the Kubernetes world, the CRDs, the custom resource definitions. So on the left, we have the inference pool. This groups our model servers. You can recognize standard Kubernetes patterns like a selector to find the pods. In this case, is app, VLLM, llama 3 8 billion instruct. And crucially, it has also an extension ref, which points to the specific endpoint picker service that will handle the smart routing logic for this pool. On the right side, we have the inference objective. This API defines a set of serving objectives of the specific request it is associated with. And currently it only houses the priority field, but it will be expanded to include things like SLO attainment and stuff like that. Now let's have a look at LLMD. LLMD, it's a Kubernetes native project that provides a distributed platform to perform inference of course, in a distributed manner. It's basically a stack of several components, and it also provides a set of default configurations, or what we call well-lit paths, for anyone to serve large generative AI models at scale across most hardware accelerators. Some of the most important features are the specific implementation of the Gateway API Inference Extension Protocol into what we call the Inference Scheduler, as I mentioned earlier. It implements the endpoint picker with specific scorers and filters based on load, KV cache, SLAs, etc. So LLMD also provides mechanisms to deploy model servers into a PD disaggregated configuration. PD means profile decode, which are basically the two phases of large language model inference. So in this case, some instances will be in charge of doing the prefill phase, and some other instances will be doing the decode phase. This is quite optimal in the sense that these two phases have different intensities, or they are the prefill is basically compute intense, and the decode is more memory intense. So splitting these two phases into different servers specialized for these tasks are much optimal. Some mechanisms like the prefix-aware caching that we will talk about are also implemented for this disaggregated configuration, and some other features, future capabilities like the variant autoscaler are coming into the roadmap and are coming into reality. So why do we need all this complexity? This slide basically shows the core problem with distributed inference. In a single server environment, life is simple, right? Inference engines like VLLM are smart and use automatic prefix caching to reduce computations and improve performance. And this is all good so far. But in a distributed environment with multi-server infrastructure, each pod has its own isolated cache. Look at the diagram, and when a request comes in, and you can see the VLLM pod has already processed steps 1 to n in what we call the KV cache. This is where we store these computations. A smart router would send this request to pod A for a fast cache hit. However, in a standalone load balancer or scheduler is blind, and it doesn't know about the cache state. It just scatters related requests across replicas. So in this example, it incorrectly routes the request to VLLM pod B, which has an empty cache. And this is what we call a cache miss. Pod B is forced to do an expensive recomputation of the entire prefix again. So this wastes precious GPU cycles and increases latency. So this is the exact problem that we are trying to solve here. So looking at this slide where we have put some numbers, the benefits of solving this problem are enormous. As the quote here states, the KV cache hit rate is the single most important metric for a production stage AI agent. Because in the end, it basically, it directly affects both latency and cost. So implementing something like prefix-aware routing, it improves up to 10 times cost savings, up to 3 times higher throughput, and up to even 100 times faster latency. So by making our router prefix-aware or AI-aware, we directly optimize all the key metrics for running LLMs at scale. So this is the evolution of smart inference routing. In this first slide, we start with the most basic setup. There is no inference gateway. This is your standard Kubernetes environment, and you have a gateway doing simple round robin, where requests A, B, and C are just scattered evenly across pod 1 and pod 2. And we established this, and as we said before, this is terrible for cache hits rates. So now this is the first improvement we introduce with the inference gateway. In this case, with a load-aware squatter. Now the gateway is smarter. It uses the load of the model server. So in this case, it sees that pod 1 is at 10% load, while pod 2 is at 67%. So it will intelligently route the next request to the least loaded pod, in this case, pod 1. This is much better for preventing hotspots, but it's not still cache aware. The next logical step, especially for chatbots, is session affinity. The gateway reads a user session header and sticks all requests from that single user to the same pod, in this case pod 2. This is good for that one user as they will get cache hits, but it doesn't help with other users. The cache isn't shared across sessions. And finally, this brings us to the ideal solution that we are proposing here, prefix-aware routing. The inference gateway now maintains a global index of which prefixes are cached on which pods. So it knows that the processed prompts A and C are already cached on pod 2. So when a new request arrives with prefix C, the gateway knows to send it to pod 2 for a guaranteed cache hit. It does this even if pod 1 is less loaded or the request is coming from a different user. And this is the most efficient and scalable solution. So with this, I leave it to my fellow friend, Cong. Thank you very much.
Thank you, Ricardo. So I'm going to take it from here. I'll try my best. So let's take a brief summary of the different approaches to this prefix cache-aware routing problem from the left to right. On the left side, the session affinity idea that Ricardo already discussed. And this is a very simple yet very effective mechanism. And this is based on the heuristic that in applications such as multi-turn conversations, each user request is built on top of the previous questions and answers, so you naturally reuse the previous context. And the limitations, of course, it only works for this sort of session-full applications. And even if you have prefix caches to share between sessions, you cannot do that. Now, on the rightmost side, I'll move on to the rightmost side. So this is actually a pretty, the idea is pretty simple. So what if our load balancer or router knows exactly the cache entries on each backend servers, and then it can make optimal decision based on the best and optimize for the global cache data rate. And this is actually also implemented as part of the inference gateway in LMD based on the so-called KV events. There's a sort of pops up mechanism that the inference engine such as LLM can emit the events of the KV cache changes, and the load balancer subscribe to those events and build that global cache. This is, of course, a little bit complex to evolve, to implement, and there's some operational overhead here as well. But in theory, this gives you the most accurate state of the cache. In the middle, this is some sort of in-between that we call it estimated cache index, that the load balancer still builds a global cache index of the cache entries of each server, but instead of trying to subscribe to some event, it tries to predict that. And the idea is simple, that the load balancer sees the request history, right? And based on that, it can guess, okay, so last time I routed a request of a similar prefix to this server, then likely this server is still going to have this cache for a little while. And this, is better than session affinity, that it achieves this automatic prefix cache sharing between requests, across sessions. And the limitations, of course, really depends on how well your heuristic is. Otherwise, you lose some accuracy. Now I'm going to dive a little deeper into this implementation of the estimated cache index. So here's a life cycle of how does the inference gateway route a request. So at stage 1, you receive a request. And in this case, we have request ABC. So here, A, B, or C represents a block of tokens, or roughly words, coming to the inference gateway. Now, at this stage of the word, we assume, so there are two pods, and pod 1 has prefix A and B, and AB cached, and pod 2 has A and AC. So at step 2, the inference gateway looks at the caches on both pods and calculates which pod has the longest prefix cache hit. In this case, pod A has AB cache already, so the hit length is 2/3. And note here that pod 2, despite it has AC, AC is not a strict prefix of ABC, so just to call it out. And then the inference gateway picks pod 1 as the best candidate, and after that, it actually updates its global index, which is basically the LRU cache, that ABC is now cached on pod 1. So here's a deeper look into how does the inference gateway actually builds that cache index. So for a prefix matching problem, we can actually think of some sort of tri-data structure. But in here, we actually choose a hash-based implementation. This aligns really well with how inference engine such as LLM manages its own memory allocation. And here we have the first block, we hash that into an integer value. Then we move on to the next block. So by the way, the block sizes are configurable. And we take the already calculated hash value of the previous block and blocks, plus the content of the current block, and then we derive the hash value of the prefix up to the current block, and we move on. Now with this, then we can build this sort of hash table that we have the hash values of each prefix, and we know which pods might have this prefix cached. And then we repeat the request handling lifecycle workflow that I just showed earlier in our previous slide. So, but we do have a challenge here for this sort of affinity-based routing that, if you have a very popular prefix and you have a lot of requests, and you're gonna send all the requests to a single server, and eventually you get the server overloaded and you get a lot of queuing, and user experience start to drop. Then how do you solve this problem? We have seen some different implementations and trying to solve this problem. For example, you can have the affinity, prefix affinity-based strategy versus a load balancing-based strategy, and you can choose that. But of course, this only, you have to choose it beforehand and doesn't react to dynamic traffic changes. And another solution is that you can dynamically, detect if a server gets overloaded. Maybe you can switch between the affinity strategy versus another strategy like load balancing. And this works really well, but the challenge of this is when you switch the different load balancing mode, you start to spread the cache sort of randomly, and then you lose the affinity. So how does the inference gateway here in LLMD solve this problem? So we want the best of both worlds. So the approach we came up with is called, we have a weighted scores framework. So we have multiple scores taking into consideration the prefix cache plus KV cache utilization plus Q plus any other factors you want to consider, and you give them different weights. Eventually, we come up with the total score of the candidates, and then we pick the one with the highest score. Just spoiler that there is a feature, and actually there is a preview feature already that we have an ML predictor-based routing strategy that learns the different signals and based on the last few minutes of data, and then predicts the best candidate based on real-time signals. Now, here's how the weighted score actually work. So, of course, we have multiple scores, we calculate the total score, and this is an example of the affinity versus spreading happening in action. So the same request and the same state of the word, but in this case, the inference gateway actually chose pod 2 instead of pod 1, despite pod 1 has a higher cache hit rate, because pod 1 has a much higher KV cache utilization at this point, and pod 2 is a better candidate. So it kind of gradually spreads the prefix to other candidates. if it has to. And this is all very simple. So, to get this behavior, you can configure via a we call endpoint picker configure API that you can configure multiple scores and give them scores. So all of these different strategies speak the same configuration language as a universal plugin configuration language. So you can even develop your own plugins if you want. So yeah, it's time to showcase this. This is some benchmarks we did earlier, running a Queen 32B model on 8 VLM pods. And with the Inference Gateway, so we look at the Inference Gateway dashboards. So with the Inference Gateway, we can see the KV cache utilization is much lower compared to the baseline, which is the Kubernetes service running sort of round-robin algorithm. Now, and we also look at the prefix cache hit ratio. With the Inference Gateway, we're able to achieve like 90% of cache hit. And with the baseline, it was barely like 50%. And now moving on to the client side observer metrics. So on the top right side, this is the time to first token, very important metrics. The kind of the first word response you get from ChatGPT response. So that's the time you have to wait. And the lower the better. So Inference Gateway kept the TTFT really low, even at very high load. And it's pretty amazing that it was like 500x faster than a traditional round-robin algorithm. And on the lower, this is the throughput, and in this case, the higher the better. And Inference Gateway was able to achieve almost 3x of the throughput with the same hardware and GPUs. So yeah, I highly recommend you try it out. So what's the stat of this? So this is not just yet another fancy kind of idea in the lab. It's actually running in production. So you get performance out of the box. And this is very low configuration overhead and very low operational overhead. Like I said, this is production ready. Tested in some of the teams internally at Google, and also we know that some other users also running this. And in the default user guides in the Inference Gateway guide, you get this out of the box. And if you want to get more, for example, PD disaggregated serving and cache management, you can move on to the LMD evaluate passes. Yeah, hope you enjoyed this so far. And some of the key takeaways, prefix cache-aware routing is a key optimization technique for large-scale LLM serving. So you should definitely consider this if you run, and if you run your inference stack on Kubernetes. So the Kubernetes Gateway API extension can extend your traditional Kubernetes gateways to be an AI gateway, and with all this load-aware and prefix cache-aware routing optimization built in. And again, with LLMD now, you further extend your inference serving stack to do smart inference scheduling, PD disaggregation, wide EP, expert, MOE models and stuff like that. Yeah, I guess I'm on time. Thanks.
Any questions? We've got a microphone over here, and if you have questions, you can just speak into the microphone, if that helps. It's over here, but I can just pass you this one. Oh, okay.
Thank you, great presentation. Is there any visibility into how a request was ranked for past requests, like any kind of dashboard where we can see, okay, this one was marked for this pod because of this ranking?
Yeah, good question. So we have a lot of metrics here. For each of the plugins that I mentioned, we have general plugin-specific metrics, and we also have logs. I mean, you don't see all the information, right? A lot of details how the information is actually made. It's very hard to present, and maybe you don't want it on your dashboard. But we have all those tracing the logs, as well as the latency of how long each step take. So you can drill down into how the decision is actually made.
Cool. Yeah, we can take a couple more questions. That's fine. Sure.
Does the prefix-aware routing take into account multi-tier offloading yet?
That's a great question. Yes, I mean, it's actually working in progress. If you go to GitHub, there's already PRs there and a proposal how to handle this problem. Yeah, so the context of this is right now it only considers the caches in the accelerator HBM, the high bandwidth memories. But you know, in the world of caching, I think it's getting evolved to multi-tier caching, such as offloading to CPU and even some other storage. The answer is yes.
And a follow-up to that, would the progress be able to handle automatically moving things between cache tiers based on what's recognized as hot prefixes?
That's a great idea. I think there are ideas and discussions around this. So how to actually do this, I think it's still we'll need to see what's the best strategy. But yeah, this is definitely in the radar.
Thank you.
Cool. I think we can take the rest of the questions in the hallway. Thank you so much, Cong. This was
Thanks.
great.